Welcome everybody. I'm very happy to be here together with Albert. My name is Niek and I'm a security analyst at Risker, where we test the security of a wide variety of embedded technologies, some of which you will see today. At the moment, Albert is a freelancer and he is open for any exciting opportunities, so please approach him if you have something like this. So why do we have this talk today? Well, we've seen in the last decade that secure boot has been broken numerous times using a wide variety of attacks. For example, one of the earliest examples is an attack performed by Bunny, where he bypassed the authenticated boot chain of the original Xbox. But probably a lot of you are familiar with the latest hacks on the Nintendo Switch, where also different people find numerous ways in order to bypass secure boot on those newer consoles. So last year, myself, Albert and Cristoforo, who is unfortunately not here, decided actually to start thinking about what is required in order to increase the robustness or the security of these secure boot implementations. So what we set out was to create a guidance for the designers and implementers of secure boot in order to up the ante for attackers when they're actually attacking these secure boot implementations. And this presentation is actually part of this. So this talk will have mostly a defensive focus, but of course we want to have some fun as well, so there will be an offensive part as well. So quickly, let's go through the agenda for today. So I will introduce secure boot, what it is, why it's needed in order to create a secure embedded device. And also I will provide here live on stage a fault injection demo. And maybe some of you can hear a beep from time to time. Don't worry, that's not an error, that's an intended beep, and you'll figure out later why it's beeping. But the real body of this talk will be presented by Albert, and that's actually how to, or what to think about when you want to design secure boot securely. And of course, we'll finalize with some takeaways that you can take home. So, whenever you have a generic device, for example, an embedded system, it's typically designed around a generic architecture. For example, you have a system on chip that includes a processor. This processor is used for executing the software. And there might be some read-only memory. This is used to store the software that's executed directly after boot. And also there's some volatile memory, for example, SRAM, that can be used by the processor when it's executing the software. So whenever this device is being turned on, then there's code executing from the external ROM, of the internal ROM. And the idea is that this ROM code will fetch the first stage from external flash, which is an external component to the chip. And it loads this in first stage actually into internal SRAM, because at that given moment in time, directly after boot, the DDR chip is not yet initialized. So one of the main responsibilities of the DDR chip, or of the BL1, is actually initializing the DDR chip. So once the BL1 successfully initializes the DDR, it will load BL2 and all the subsequent stages up to the user applications that are executed from DDR. So with this design, there's two major threats. The first threat is that if somebody has access to the device, so it can open it and reprogram the flash, it is possible to actually reprogram this chip in order to take control of the device, because the code that will be executed is stored there. In a very similar fashion, malware that entered the system remotely, to, for example, a remotely exploitable vulnerability, can do the same by reprogramming the flash from software in order to create a persistent foothold. So even though you reset the device and the malware is wiped from memory, it will still be initialized during boot because the malware makes modifications inside the external flash. So this is the primary reason why we need such a thing like secure boot, in order to guarantee that the software that's stored in external flash is actually authentic and not changed by an attacker. So the basic idea is that you have a root of trust that's embedded in hardware. And this root of trust often consists of read-only memory, the code, and some secure storage, which is also typically only readable. So what is often used is OTP, so you can write it only once. And this combination together allows you to authenticate all the code that is actually loaded, authenticated, and executed and stored in external flash. And optionally, if it's important, you can also assure the confidentiality of the code and data by actually decrypting the stages that are loaded from external flash first. And this means that the code and data that is stored in external flash needs to be encrypted. So how does this typically work? Well, the idea, the hardware architecture doesn't really change too much. So next to the stages that are stored in external flash, a signature is stored. And actually this signature plus the stage are loaded into the internal memory for the first stage. And then this signature is used in order to authenticate the authenticity of the BL1. And this allows the ROM code to identify if something has changed in the flash or not. So if something changed, the flash will the ROM code will actually not continue, and it will only continue to boot BL1 if the image is valid. So next to modifying code in flash and data and creating a persistent foothold, there's other threats as well. For example, secure boot prevents attackers to escalate privileges. For example, when you can write to the flash, for example, when you have control of the Linux kernel, it prevents you from changing any code in the flash that is executed at a higher privilege level. And also this allows you to prevent access to keys, code, and for example, cryptographic engines that are used by the system. And moreover, when you have a secure firmware update mechanism, which is fundamental for a secure device, if you do not have secure boot, you cannot guarantee that anybody is not making any changes in the software that's being programmed during this firmware update to the external flash. So the real world is a little bit more complex. So there's a lot of stages that are run consecutively after each other, and the authenticity of these stages need to be guaranteed. So what you typically see for these stages is that they're running at different privileges. So the early boot stages are running at the highest privileges, whereas the user applications at the end are running at the lowest. But also some of these stages cannot be changed. For example, the read-only memory, the first code that's executed after boot. If there's any vulnerability in there, you cannot change it anymore. Whereas for the later stages, you can actually change vulnerability, or you can actually fix vulnerabilities by updating the software. And also, all these stages, part of this boot chain, they're actually made by different parties. So that means that the developers responsible for implementing these stages are different. Therefore, you can already assume that probably the security standard of these stages is probably different throughout the chain. So all these facts together result in the fact that it is very difficult to make sure that this entire chain is completely secure. And even more, if you think about the constraints of secure boot. So you need to initialize an interface with hardware, which can be complex and error-prone. You need to think of performance, because you do not want to wait 10 minutes for the device to completely boot. There might be customer needs which you need to adhere, which increase the complexity of the system. You need to make sure that the device is recoverable. So for example, when the flash gets corrupted, you need to have an interface that allows you to reprogram the flash with a valid image again. And also, at the end of the day, you want to keep the engineering costs low, so you cannot spend too much time in actually making sure that this chain is fully secure. But we would like to stress that it's very important to get this right, because bad security is very expensive. You can already imagine if there's a vulnerability in your ROM code and you cannot change it, that basically means you can throw away the chips because you cannot sell them anymore for secure products. And this probably has an impact on your PR, and you might have to spend money on crisis management. You might have to recall devices that you cannot sell anymore, or you're left with them in your stock. And also, all these things have an impact on the time to market, and all adds additional engineering time, which makes it more costly. So it's a good idea to think about creating a secure boot chain from the start. So I think everybody agrees that we need to create a secure boot implementation. But where do you start? Well, that's exactly what we're working on. We're working on the guidance document that actually gives you a few ideas what to think about, what is required to design secure boot. So these guidelines can be used as a start for when you're designing or implementing secure boot, because they, in a practical manner, very concretely tell you what you have to think of. So let's start using them to secure boot. Well, before we do, we're actually gonna have some fun first. So what we're gonna do here live on stage is a fault injection attack, which is a hardware attack. And fault injection is about introducing faults into a target in order to change its intended behavior. So I think everybody here knows that an embedded device includes a chip that's executing software. And this chip actually needs a stable clock signal in order for this software to execute. And the same holds up for the voltage that is supplied to this chip. And both these signals need to be between certain boundaries, because otherwise it's not guaranteed that the chip will function as intended. And this is exactly what we're exploiting using fault injection. We're actually running the chip for a very brief moment in time outside of its intended conditions. And by injecting these glitches, we can change the intended behavior at a specific moment in time. And you probably realize if you do this at a security critical moment in time, you probably can compromise the security of the device. And that's exactly what we're doing here. So in order to inject these glitches, we need to have a device that's able to provide an arbitrary voltage signal to the target in order to pull the voltage down at a given moment in time. And that's exactly what we're using here, which is the Risker Spider. But nothing prevents you from using easier to access tooling, for example, like the chip whisperer. They may not be able to inject the same type of glitch, but they definitely are capable of injecting the same type of fault in the target, which allows you to compromise the security of a device. So we interface with our tooling using a laptop that's laying here in front of us. And most importantly, of course, we need a target. So we're interfacing with the target using a serial interface. And the target that we're using is an STM32F4 development board. And even though this is a development board, it's still a relevant target because there's definitely secure embedded devices that are using these chips. For example, there are several hardware crypto wallets using this chip in order to protect the keys for the user. So like I said, we're doing voltage fault injection, so we need to provide an arbitrary voltage signal to the target. And in this case, we're not doing that by providing power to the USB port, which is the intended way of powering this device, but we removed a few components from the board in order to supply the power directly to the power domain that is responsible for powering the subsystem responsible for executing software. And this is, as you can imagine, the ARM core inside. And because we are targeting secure boot, we need to reset the device every time, because secure boot, hence the name, only executes during boot. So we simply hook up also a reset line to the system reset exposed on the development board in order to reset the chip every time we start. So everybody knows that does some hardware hacking, knows that once you start doing this kind of stuff, even though the setup can be quite simple, the amount of cables go everywhere. And during this presentation, I do not have the time to explain you everything, all the ins and outs about this setup, but please come to Risker's booth where this setup will be running so we can discuss in more detail what exactly is going on here. So a good question to us is always, what happens exactly when you start injecting these glitches? Well, that's not too easy to answer. And academia has been researching quite a bit in order to figure out what exactly goes wrong in a chip. But unfortunately, you do have only limited access to the internals of this chip, and you do not get a lot of feedback. But one thing we achieved over the last few years is that behaviorally, you can make a few conclusions. Because one of these conclusions, one thing we know for sure that's true, and this holds up for all architectures, is that by injecting these glitches, we can actually change the instructions that are being executed. And we refer to this fault model. And there might be other fault models actually in play. We refer to this fault model as instruction corruption. So the idea is glitches can modify instructions. It is really great for modifying code because you're changing the instructions, makes sense. But it's also very effective in either getting data out or getting control of the target. And the key point here is that because we can change software, we can use this to break any software security model. Because if an embedded device relies on a software security model, which is implemented in software, hence the name, then by changing the software, this model is completely gone. And that's exactly what we will do here live on stage. And the basic idea is that if you, for example, look at this ARM instruction, which has a certain instruction encoding. So by injecting these glitches, we can impact this instruction's encoding. And by doing this, we can either change the opcode or the operands that are used by the opcode. So in this case, a simple example would be, for this add instruction, is that we add two different registers and store it in the original register by only changing one bit. And as you can see, the last bit in this encoding is changed. And that's exactly the granularity that you can have with fault injection. You really can change single bits in a single instruction. So let's use it to bypass secure boot. So in this case, the development board that we have laying here in front of us is a microcontroller that is executing after you reset from internal flash. So BL1 is stored for this demonstration in internal flash. And the code protection feature is enabled, so an attacker cannot change the BL1. The only thing that the attacker can change is the code that's stored in external flash. So for example, the BL2 and whatever is executed afterwards. So whenever this device is released from reset, the BL1 is actually responsible for loading, decrypting, and authenticating the second stage bootloader, BL2. So in code, it is roughly implemented like this. So we copy the image from external flash into internal flash. We decrypt the image there. So now we end up with plain text. We copy the signature. We calculate the hash over the copied image. We retrieve the hash from the signature using a public key. And now we compare both hashes. And the idea here is that these two hashes are not the same, then something has changed in BL2 that's stored in external flash. But if these two hashes are the same, we go to the next step and we actually successfully execute the image that's being loaded from external flash, because this image is valid. So how do we attack this? Well, like I said already, we can only change the code that's stored in external flash. So we override the BL2 with our own code. And in this case, we do not only put code, we also put pointers. And it's important to know that these pointers actually point to the internal SRAM buffer. And this allows us to execute our code. And I will explain how this exactly works. So the original BL2 image, without changing anything, looks somewhat like this. So it's completely encrypted. There's a high entropy, you don't see any strings, you don't see any code. And once you turn this device on, it prints the following on the serial interface. BL1 says successfully started, BL1 says loading BL2 successfully, decrypting BL2 successful, authenticating BL2 successful, and then it indicates it will jump to BL2. And then BL2 says, hello, I also started. Now, the modified version, so what an attacker will do, putting the code and putting the pointers there, the behavior on the communication channel is different. Again, BL1 says successfully started. Again, it says loading BL2 successful. Again, it says decrypting BL2 successful. But then at the authentication step, BL2 actually says something else, because it identified that the image actually changed, and it actually stops executing. So when do we actually inject the glitch in order to make this attack work? And the idea is, of course, as you already can imagine, because the code is copied to the internal SRAM buffer, somehow we want to load one of those pointers into the program counter in order to take control of the device. So what we are doing is actually we are injecting the glitch at the moment in time when the BL1 is still copying the data from external flash. And we wait actually until the code is successfully copied, but is only copying the pointer still, which is put at the remaining image. And by doing this, we can load one of those pointers into PC. So basically what we're doing is we're hijacking the control flow directly from the mem copy. And because we hijack the control flow directly from the mem copy, we bypass the decryption step and the verification step using a single glitch. So let's do this. I will switch to the other laptop. I hope this cable will reach.
Dan moeten we even tussen. Yep.
Okay, what we're looking at now is a oscilloscope. So what we're seeing here, this is the actual reset line that we use in order to reset the device every time before each experiment. So whenever this line goes up, the system is actually kept out of reset. So I can also show you another signal, which is actually the power that we provide to the target. And this is actually the voltage directly supplied to the power domain of the ARM core. And we're roughly powering the device with 1.1 volt. And what you see here already, you see it sometimes happening when it triggers correctly. You see this thing. And this is exactly the glitch that we are injecting that allows us to change the intended behavior of this glitch. So what else I can show you is that we are interfacing with the hardware that's laying here in front of us using a Python framework. And what's happening here is that for each experiment, we just record the communication on the serial interface. So I'll briefly walk you through the columns. So there's the ID. So that means that since we set the setup here, we performed roughly 2,000 experiments. The glitch delay is actually the time we wait from the moment we reset until the glitch is injected. The glitch voltage is actually how far down we go with the glitch. So this is shaping the depth of this pulse. And the glitch length is basically how wide the glitch is. So the combination between glitch voltage and glitch length determines how strong the glitch is. And here in the data column, we actually see what's being returned. So I can briefly stop this. As you can see, for the green experiments, the target actually responds with all the expected strings because it's finalized with authentication BL2 unsuccessful, stopping because it detected that the image is different. And for example, for this experiment, we see that there's only a small string being printed. That means that probably the combination between glitch voltage and glitch length is too strong and the device could not continue. So that's not exactly what we want. Another interesting thing is, for example, this experiment, which was really in the beginning of the campaign, you see that somehow a stack trace is being printed. And this is actually the internal state of the CPU. So by injecting these glitches, we actually crashed the CPU, which is interesting, but we're not after crashing the CPU. We want to actually execute our own code. So for the ones that actually heard the beep from time to time, every time you heard a beep, then actually the following happened. You see actually that BL1 has successfully started, but directly afterwards a completely different string is being printed. And I can tell you this string is actually printed by the code that we put in the external flash instead of BL2. So this showed that we actually can completely hijack the control flow and execute arbitrary code instead of the original code. So what we typically do is we typically plot the results in order to figure out if we can play with the glitch parameters in order to make it more successful. So we made a previous plot where it is shown that on the top, all the green experiments, these are the ones where the glitch was not strong enough. All the yellow experiments where the glitch was either too strong or it caused another type of fault in the chip that made the chip stop operating. But you see that at certain intervals, these red dots appear. So these are all the sweet spots where the combination between glitch delay and glitch voltage resulted in a successful glitch. So if we would change the parameters of our campaign to one of those sweet spots, we will probably bypass the secure boot implementation constantly. So the setup will continue beeping, and that means that we're bypassing encrypted secure boot at every beep. Let's wait 1 second. So concretely said, what's going on here? So we actually turn encrypted secure boot into plain text unprotected boot using only a single glitch and having no knowledge of the encryption key whatsoever. So we don't really need it for this attack. So why does this work? Well, we're actually performing an attack that we described in our 2016 paper, which is called Controlling PC. And actually, there we showed that it's possible to glitch controlled values directly into PC in order to hijack the control flow. So the basic idea is that we actually change the intended behavior of the copy loop that's being used to copy memory from A to B. So on ARM, how this is done is using load and store instructions. So this is the actual copy loop that's also running on the target. And what we're actually doing is we change the intended behavior of the load instruction. So instead of loading the data originating from external flash, which are going into internal registers, and from the internal registers going to internal memory, we're actually not loading the values originating from external flash to the intended registers, but we're also loading it to PC. By just flipping a single bit, we can load one of those values into PC in order to hijack the control flow. So the demonstrated attack in its current form is specific for ARM32, because some of you are probably aware that ARM32-bit is one of the few architectures where you can load a value directly into PC. Most other architectures need to do this indirectly. However, that does not mean that variants of this attack are actually also applicable to the other architectures as well. So is this the only secure boot attack you can actually do on secure boot? Well, no. So we also are working on an enumeration of the different type of fault injection attacks you can do in order to bypass secure boot. And this will also be released somewhere after this presentation. So this was the offensive part for now. And I would like to give the word to Albert in order to tell you what you can do in order to increase the security of secure boot.
Hello. So Niek just gave us an introduction on secure boot. And also gave us a very nice demonstration of an advanced attack in which encrypted secure boot can be bypassed. So how could we protect against this? Well, before we even start talking against protecting against those kind of attacks, we need to get the fundamentals right. So what do we consider the secure boot fundamentals? Well, we need a hardware root of trust. We need to authenticate everything. We need to encrypt everything. We need to use strong cryptography. And we need to use that cryptography correctly. And I guess you all agree, right? But in the real world, things can go wrong. So for instance, for the hardware root of trust, how many of you know any devices that actually don't have ROM or one-time programmable memory? And actually, for Intel, we actually know, so Intel on the desktop, we actually know that their root of trust is actually SPI flash. So what about this authenticate everything? So let's say we have, some data in flash. We have a header followed by BL1, followed by the signature of the BL1 and the header. So how does the ROM code actually know how much data to copy in? Well, that's stored in the header. The header consists of perhaps how long the BL1 is, where the destination in SRAM, where perhaps that the code will be copied, maybe also an entry point of the image. But now we have a problem, because these values will now be used before they are authenticated. So the ROM code will first copy this length, so this entire header, and it will use that length before it is authenticated. So you can see already things going wrong. So if that length value is not checked, maybe you have a buffer overflow. If you don't check the destination pointer, perhaps the attacker can overwrite the stack. So of course the solution is actually to use a signature on the header and verify this before using any of these values. Okay. So in addition to actually having to authenticate everything, and in this case we mean authenticating the code, authenticating the data, and authenticating the metadata, it is also important that a design enforces that basically everything is authenticated. And this is basically to prevent mistakes from people, from people making mistakes. So a real-world example of this is actually AMD Secure Boot. So their design allows them to not authenticate all the code or all the data. And this actually directly leads to basically a secure boot bypass. Okay, so we were discussing some of these things we should do, and we suggested, encrypt everything. But then Niek said, are we actually proposing security by obscurity? And, well, to some degree, the answer is yes. So why are we proposing this? Well, there will be software vulnerabilities in written code. So this is, some way to mitigate this. And basically, it makes analyzing the firmware more difficult. And additionally, some attacks may actually be more difficult to perform if you don't have access to this firmware. So for instance, return-oriented programming attacks may be more difficult. All right, so I think we could agree that these fundamentals make sense. But how else can we actually try to make a nice design? Well, I think one of the classic rules is to keep things simple. So nobody actually wants to have very complex parsers during boot. So nobody wants to have signatures in X509 certificates with ASN1 parsers, which you have to write yourself. And I think it's always a good idea not to actually try to support everything under the sun, especially in ROM code. Because this makes auditing easier, not just for guys like us, but also for the developers actually writing this code. They will be able to understand it better and see where things can go wrong. So a nice real-world secure bypass is actually a U-boot vulnerability in the file system parser. And file systems are typically actually quite complex, so it's easy for a bug to creep in. So the next rule we have is to drop privilege as soon as possible. And when we normally talk about dropping privileges, people typically think about things like, monitor mode, hypervisor mode, kernel mode, user mode. But we also mean things like access to keys, access to ROM code, access to crypto engines. So for instance, there is actually no need for each successive stage of secure boot to have access to the keys of the previous stage. For instance, there is no need to actually have access to ROM code after the ROM code has finished executing. And it's also important that keys are cleared, for instance, from not just memory, but also crypto engine registers. Okay, so let's assume our design is fantastic. However, implementations and software will probably still have vulnerabilities. So, what is the typical mitigation for these software vulnerabilities? And especially if we look at, maybe some other places where people have a lot of experience with this, it's basically, desktops and servers. So basically, it's about exploit mitigation. And basically, the binaries are hardened by the compiler, sometimes with a little bit of help from the operating system. And we're talking about things like stack cookies, write, store, execute, ASLR, CF-fine. Okay, so I now have a question for the audience. Could I get a show of hands how many people know what most of these things are? Come on, there must be more people. There must be more. Okay, so a fair couple of people. So of those people, or anybody else, do you think actually those mitigations are actually used during early boot stages? For instance, ROM code. So could I get another show of hands? Who thinks some of these mitigations are actually used? No one? No one? Okay. So actually, that's pretty correct. During early boot stages, for instance, ROM, typically there are no stack cookies. ASLR is not implemented. Control flow integrity, not implemented. And all this memory protection stuff, not implemented. And what this actually means is that if there is a software vulnerability in the ROM code, it will actually be easy to exploit. So, I mean, come on, it's 2019, right? So, I mean, you practically get things like stack cookies for free. If you tell your compiler that you want code with stack cookies, it will give it to you. All you have to do is then actually provide the randomness needed for that stack cookie. So something like control flow integrity, you can still get from your toolchain. It's quite fiddly to set it up, but it's still something the toolchain can give to you. So if you have to use something like memory protection, you will have to set it up yourself. So if you want to implement write, store, execute, maybe with a memory protection unit or a memory management unit, depending on which one's available, you will have to write this yourself. But this, for instance, protects the system from the processor being able to execute that, for instance, code code that's on the stack, or overwriting memory that's already executing. During boot, not only can the processor write, but also peripherals with DMA access could perhaps overwrite the stack or already running code. And therefore, it's probably a wise idea, if one is available, to use an IOMMU or an SMMU on ARM. Okay, so let's take a step back. So what actually about all these hardware attackers? What about these fancy attacks, for instance, that Niek demonstrated? Well, actually, already all the things we talked about now about software, everything still applies. These attacks are available for software, for hardware hackers. However, there is also a little bit larger attack surface. So, for instance, the attacker will still have access to the physical board, and this means an attacker can actually tamper with signals on this PCB. So therefore, it's a very good idea that you first copy data from external flash into internal memory before you verify it, and then only operate on that internal copy. And this actually prevents double fetch vulnerabilities. So imagine, for instance, that the ROM code authenticates all the data in flash, but then when it wants to use it, it fetches it again. Now, if you have a flash emulator, you can actually give a different response the second time. And this means you can actually probably exploit things like, buffer overflows. Okay, so, based on that, I think to defend against these hardware attackers, you need to lock down your hardware. And it's important that peripherals which are not used are turned off. So for instance, if you're using SPI NOR flash, you should probably turn off the NAND interface. NAND is typically more complex and has a higher chance of vulnerabilities. It's also a good idea to actually turn off flash access unless you're explicitly copying data from that flash to internal SRAM. And this will actually cause you to detect these double fetch vulnerabilities during development, where you can still quickly fix them. And of course, you still need to protect, so password protect or turn off JTAG and other debug ports. And finally, it's important that debug messages on the serial ports are actually limited or turned off completely. So not only do these messages give an attacker a better idea of what's happening, they also give a better idea of when they are happening, which, as we saw in Niek's demo, is quite important. Okay, so, what about hardware attackers who actually have access to more than perhaps just a soldering iron? Is this, are we only concerned with these fault injection attacks? Or perhaps, should we also care about maybe side channel attacks? So maybe to give you a nice idea of what a side channel attack is, it's basically you find another channel of information to give you more information about what the target is doing. So in Niek's demo, he actually also took a power trace, so a power measurement just after boot. And actually that's what you can see here. And this is what the power usage looks like when a correct image is being booted. So we changed a couple of bits in the image, and we now power it on again, and we actually get this power profile. And we can actually see that the power profile at the end has actually changed. So this is probably a nice region to actually start injecting those faults. So is this the only way we can really use a power side channel or other kinds of side channels? Well, no. So for instance, we can use timing attacks to recover and forge HMAC and CMAC signatures, or MACs. So a real-world example of this is actually the Xbox 360. Or we could, for instance, use differential power analysis to attack and recover encryption keys. For instance, at this conference, there was already actually a training on how to perform these attacks. So therefore, if we think about how we need to make a design, we need to basically, expect that these secrets will not be secret forever. So a nice design will probably use something like RSA and ECC instead of relying on HMACs or CMACs. Okay, so, you're now thinking, these are PHY attacks, these SCA attacks, are they this expensive? Niek showed us some of the hardware he's using. That looks quite expensive. So the question is, does it always have to be expensive? And actually, fault injection and SCA do not always have to be expensive. So what we see here is actually a PCB which we call the horoscope, designed by me and Alyssa, that actually does both fault injection and SCA. And it only costs about €5. So mind you, it's pretty horrible, but it works. And in fact, if you have any development board lying around at home, which has a fast analog to digital converter and some GPIO pins, you could actually pull some of these attacks off yourself. And if this is too fiddly for you, hopefully at some point in the future, the chip Whisperer Nano will become available for something like around $50. Yeah. Okay, so I think we can conclude that actually SCA, and especially fault injection, are actually turning into real threats. So let's try to make it harder to actually inject these faults. So what will be our goals when we try to mitigate a FI? Well, the first goal would actually be to lower the probability of a successful attack. And if we can lower the probability of a successful attack far enough, it actually means it's infeasible. It will just take too much time to actually get a successful glitch. So let's try to harden some hardware against these fault injection attacks. Some chips. Let's try to harden chips against these attacks. So the first thing we could do is basically add redundancy. So for instance, on the ARM R line of microcontrollers, there are actually multiple cores operating in lockstep. And when any mismatch in behavior between these cores is detected, the device can reset or an exception is generated. We could also checksum all the data before it is used. We could introduce things like clock jitter, which basically means using an unstable clock to make the timing not constant anymore. And this makes it a lot harder for an attacker to predict when a glitch needs to be injected. And you could also add things like glitch or fault detectors. So a glitch detector tries to basically detect the glitch as it's being injected into the device. So for instance, something like laser fault injection exists, which basically means shooting at a chip with a laser. So if you want to protect against that, you can actually add things like light sensors. You can also try to inject the fault when faults have already occurred with a fault detector. Okay, so it turns out that there's actually a lot of academic research in this topic. And if you want to start reading up on these kind of things, we really recommend the Sorcerer's Apprentice Guide to Fault Attacks as an excellent starting point. Okay, so these countermeasures sound great, but they also have a couple of challenges. So it turns out that actually hardware is fixed, and getting people to change hardware can actually be tricky. And even if you can get people to add, let's say, sensors, that might actually increase the costs of these chips. So if you, for instance, want to use these light sensors, you need to add light sensors to every critical component that you want to protect. Now, these things take space, and that basically means you need a bigger die. If you have a bigger die, that basically means your per unit cost is going up. So, another downside is that if you have these detectors, they need to be calibrated. And if you make them too sensitive, you will basically get returns in the field. People will have unstable devices and will just send them back to you. But if you don't make them sensitive enough, basically you're not going to be detecting the glitches. So therefore, we feel that fault injection resistant hardware is not yet realistic for actually most devices. Okay, so then the question really becomes, what can we actually do without modifying hardware? So let's, for instance, try to make bypassing a hash check, more difficult. And we'll only be trying to use software and hardware that is actually commonly available in chips. All right, so what we're going to do is we're going to try and make bypassing a single check hard by basically adding more checks. So we're going to go through our source code and we're going to identify all critical checks. So this doesn't mean just hash checks, but it can also mean things like checking the length of pointers, checking the length of values, checking pointers, and all these security critical operations. And then basically we're going to perform these checks multiple times. So basically, here is the flow we kind of already saw from Niek's description. So first we reset the chip, then the image is copied, we verify that image, we calculate the hash of the code, we recover the hash from the RSA signature, and then we check these basically twice. And if we do this, the probability for success will actually drop by quite a lot. So another thing we could do is actually introduce random delays. And these are actually just, for loops with a random number of iterations. And basically their goal is to randomize critical checks in time. So Niek said, I should add a random delay. So, just after I reset the chip, we add a random delay. And hopefully the probability for success will likely drop. So, unfortunately, that wasn't the case, because what goes wrong? Well, it turns out that this copy image operation actually has some SPI activity. And this SPI activity is basically, this external digital signal. And actually, an attacker can use that digital signal to actually just, to time when to inject a glitch. So, basically, our check is now at a constant offset from that digital signal. Basically, the random delay has been removed. Okay, so it wasn't a great idea to put it directly after reset. So what about adding it after this copy image? I mean, after that point, there aren't any of these digital signals, right? Yeah, unfortunately, this is also not perfect, because the verify image, these RSA computations, these SHA computations, actually have quite a distinct power profile. And if an attacker is advanced enough, and has, for instance, a very nice oscilloscope, he can actually trigger off of that power profile. So basically, for an advanced enough attacker, that check is still at a constant offset from that trigger. All right, so of course, we should have put that random delay just before that critical check. And this actually ensures that even if that critical check has perhaps a distinctive power profile, there may not be enough time for for all this equipment to actually see that trigger, introduce a glitch, the glitch to propagate to this device, and this glitch to turn into the fault, because the operation will have already finished. All right, so I mean, these ideas by themselves are nice, but maybe we can really make them a lot better if we actually try to combine them. So, I tried to combine them, I added random delay, and I added two double checks. So, what could we improve here? Well, it turns out, yeah, sure, these checks are now at random points in time, but the second check is actually still at a constant offset from this first check. So what we, of course, should have done is added two random delays, because both of these checks are critical. And again, if we do this correctly, the probability for success actually drops significantly. All right, so this was like, a nice simple example. Let's actually try to combine some more countermeasures, some more mitigations. So what we're now going to try and combine is write XOR execute combined with multiple checks. Because basically, we want to mitigate the attack from Niek's demo. Okay, so this is more or less the code Niek already showed you, but I've added an extra check. So once again, we'll first copy the signature. We'll first copy the signature and the code. We then calculate the SHA hash of it. We'll then retrieve the hash from the RSA signature, and then we compare them twice. And if they both match, we boot the image. All right, so now let's add this write XOR execute protection. And before we do anything, we first make this region of memory where we're going to copy all this data, we're going to make it basically read-write, which means we cannot execute code from that region. And only then do we actually copy this data into it. So again, if we were to now glitch during this copy, as Niek demonstrated, we would no longer actually be executing our own code because that region of memory is not allowed to be, is not executable. All right, so we then continue booting. So we still perform this SHA operation, this RSA operation, and then after the first hash comparison, we actually make the memory region executable. And then we check the hash again. And basically only when these two checks have passed do we boot. Okay, so why is this nice? Well, basically the control flow can no longer be hijacked at the mem copy. And that is because the code still needs to be made executable. And we're actually now enforcing that multiple glitches are required to bypass secure boot, which makes it a lot harder to bypass. All right, so these are just some examples of the ways we could improve secure boot, also by combining mitigations. And we think there are actually still a lot of options in creative ways these mitigations can be combined and stacked. So our key takeaways for today are that we believe that secure boot design is actually hard, and it's actually hard also for the experts. And we really believe that the smart secure boot design will actually save money, not just in the long run, but also in the shorter term, because it should be easier to implement. And actually, we think that software mitigations can actually be implemented very cheaply, using hardware that's actually quite commonly already available. We also believe that stacking different mitigations on top of each other actually makes them a lot more effective. And finally, we believe that actually testing needs to be done to actually verify that the implementation is secure. All right, so thank you. This was our presentation. And just before we go to questions, we actually have a question for you. So do you think that secure boot implementations can actually be improved significantly without significant costs?
One question.
Okay.
I think these days the companies are recommending using TPM chips for secure booting implementation. How different that is compared to this, what you're recommending here?
So I think that's a good question. And I think that if you have a TPM chip, I think a nice TPM chip actually still relies to some degree on secure boot not being broken. So I think actually they're quite complementary technologies. Are there any other questions? So before I answer that question, also come visit perhaps Risker at the booth, and during the upcoming days, ask us these questions or perhaps answer this question for us. Sorry, yeah.
Hello. Yeah, I have a question. Okay, first of all, very nice talk. We really liked it. Say we have requirement in terms of booting time, right? And we work with real-time systems, so it has to be booted in X millisecond, whatever the value of X is. And when we do secure boot, out of that X, 30% is taken by the RSA signature itself. And then some more operations that you have to do. So did you do any measurement that, say, for example, you have given different mitigation tactics using the software tactics and then multiple checks. Did you do any measurement that how much overhead it adds? Because whatever techniques you add, it will add to the code size. It will add to the, the execution time as well.
Okay, so
I have to still meet X.
Yes. So I think the question is basically, you need to basically meet some of these performance requirements. And I think one of the key points you already said is that RSA takes a long time to compute. So I think the nice thing about some of these mitigations we presented is that this RSA computation and these SHA operations may take quite a bit of time. But actually that check at the end, you're just checking, let's say, 20 bytes, 16 bytes. That's not going to add that much overhead.
Along the way, he will pick up others.
I mean, my question is, I assume it will not take much of time, but you have some random delays, so that will also assume some time. My question is, did you do some measurement that what could be a typical percentage increase in the cases?
Yeah, so it's a very good point. And honestly, if our paper would be academic, it would be fundamental to dive into the overhead of what these different mitigations actually do. So our guidelines are mere a indication what you can think about. And honestly, I think as an implementer or designer, you need to cherry pick because also if you think about this overhead, it depends on what kind of device you have. So it's very difficult to reason about this in a generic fashion. We took the approach of not diving into the overhead, but just giving an indication what the possibilities may be. but we are very well aware of the constraints, like they're also already mentioned at an early stage in our talk. So we are not advocating that you have to do all the things we say. We like to advocate, think about it, what the possibilities are. And in your environment that you're working on, apply what makes sense. Because also, it's not about making the attack impossible. It's about making the attack too complex or too difficult to perform. I hope that answers your question.
So maybe a slightly different way to also look at it, you can also say, well, I have this performance budget. That basically means my random delays can be up to this long.
Hi. I guess the random delays you'd introduced were to basically bypass fingerprinting of power profiles and timing attacks, right? How do you prevent them from being used for time of check to time of use vulnerabilities? And if not, to what extent do you consider that just a valid trade-off?
So I think these are slightly different subjects, but I think like these double fetch issues you would typically identify basically by the activity you see basically on the SPI bus, on the NAND bus. So I think these power side channels and also these SPI activities are basically some different side channels you actually have to try and identify what a target is doing. And there are some cases where you use one and some other cases where you'd use the other.
Just to clarify, I agree that they're entirely different scopes of attacks. What I'm seeking to understand is more about how the timing that you've introduced, how do you prevent that from just enabling another side channel attack? Or do you just consider that not really a concern? Perhaps I could connect with you offline.
Let's discuss this in further detail after the talk, because I think it's an interesting thing, but I don't think we have a good answer right now. Was there's here a question, I think, and there a question, and there a question. Who's first?
Hi. So you're mentioning about using write exclusive or this one execute permission for mitigation, but I was wondering if the attack is on hardware itself. And then the physical memory itself, what is the purpose of having such a security? Because that will be consulted from the software layer. So
it's a good point that you need to be executing from virtual addresses in order to implement the write or execute using the MMU. So that is indeed a requirement. You need to be switching from physical addressing to virtual addressing as soon as possible.
So in the fault injection attack, you are demonstrating the attacker is directly operating on the physical memory, right?
Yes, but that's only for this target. So this target is not using an MMU in order to translate the addressing. You want to add something?
Yeah, maybe also to clarify, even if you have physical and virtual mappings, they can also just be one-to-one.
Yeah.
So that the virtual address is still just the physical address.
So
and then on top of this, you can still use those permissions.
So if as an attacker, I try to inject a fault and flip a bit in the physical memory, will NX, the concept of NX will it be able to anyway prevent me from doing it? Because I am not running any software code or anything, right? So.
Yeah, so I think, I'm not sure I understand the question, but what I think you're trying to imply is, yes, you could use a fault injection attack to actually also change those permissions. But this actually requires a lot more sophisticated attack than actually just corrupting instructions as they are fetched from memory. I'm not entirely sure if that answers the question.
I think that was not the question. The question is more like, so in if write or XOR execute is enabled, and if from software I'm trying to execute a page which is not executable, then the processor, the hardware will say that this protection is enabled, and the page table will, or whatever technology is used, will say that this page is not executable. So combine these two, it won't execute. So that is from the assistance from the software that we're enforcing it.
Yeah.
But now I'm writing directly to the metal. That is, I'm changing the magnetic or the quantum state if it is flash. So that means there is no software involved to stop me from writing it.
Let's also take this discussion for after the talk. We're very happy to continue this, but I think we have to hash out a few details what you mean exactly.
Sure, yeah.
Uh, Related to the topic of secure boot, we have to do over-the-air updates quite often. Just wanted to know, have you studied the security of secure boot at the time of an over-the-air update? And do you have some recommendations for that?
Yeah, so how I look at it, and it might be wrong, a bit different from Albert, is that any path, including the firmware update path, you need to do that in a secure fashion. So depending how you do the over-the-air update, the interface for this over-the-air update needs to be implemented using authenticated code. So probably on your system there's a binary running that allows you to perform this firmware update. And then basically what the firmware update does is it just programs the firmware update to flash, because that's where it's stored when the device is off. And what is your question then?
Yeah, so do you have any recommendations? Because that's a time when the signatures are going to change. You're going to have new code that's coming into your flash.
Yeah.
Yeah, so do you have any recommendations?
Okay, so typically these signatures you have, are already in the over-the-air update, and will actually be just, so the new signatures will actually directly perhaps overwrite just the old code with the new code, and then the old signature with the new signature. Then I think a recommendation we can add is that you actually verify also the signature before you start writing, because if you already start writing and you know you have an invalid signature, you may end up with a device that can no longer boot.
Okay, thank you.
Hey. Hello. Hello to both you guys. My question is in the part where you use the voltage to obstruct the opcodes. So I understand the part where you can obstruct them, but I did not quite get the part how you modify them. How does the instruction change by using voltages?
Yeah, so by injecting these glitches, you can make changes in the intended behavior of a chip. And in the end, when an instruction is being executed, it's first fetched, then it's decoded, and then it's executed. And in this fetch, in this cycle, a lot of things can go wrong, because in the end, the fetch is that the instruction will travel over a bus. So when the instruction is traveling over that bus, it might be changed. When the instruction is being decoded, there's some hardware responsible for doing this decoding. And this is typically consisting of flip-flop, which also can change. It can also differ there. But this is what I meant with it's very difficult to know exactly what goes wrong, because behaviorally, it does not matter if you change it during the fetching or during the decoding. Because the resulting instruction, so the instruction that it's modified into, may be very well the same.
So maybe to add,
let me clarify with an example, my question with an example. So you demonstrate a part where you're loading into the registers, and then a glitch can lead that load to actually load into a program counter. Yeah. How does that happen? Okay. I would understand if the load doesn't happen at all.
Let me try to explain it, and if you're not happy, we can also talk afterwards. So imagine, there's this bit value, there's this instruction traveling over a bus, right? And, buses are quite long, and they use a bit of power. So then we, pull out this power. So that instruction is traveling along, and maybe some of the bits flip, maybe from 0 to 1 or from 1 to 0. And we really can't control which bits will fall over, right? We're just hoping that one of these bits falls over, or flips, or actually turns on in this case, so that one bit which says I also want to copy data into the PC register, that bit is turned on. So in a lot of cases,
it works in a hit and trial basis, is what you're saying.
Yeah. And actually, if we look at the plots, you can actually see that there is some relationship also with how low you pull the power and what happens.
Okay. Yeah. Thanks. And the other part is the device which you are using on the as a peripheral to the board, without any modifications to the power supply units. Does that work without that modification? You probably would also need access to the hardware circuitry, some sort of modifications to the circuitry, right?
Yeah, so for this particular target, there's definitely modifications made. So one of the things that you typically want to do is you want to remove the decoupling capacitors, which are actually on the PCB to flatten out the power that's coming in. And that's exactly what you do not want when you start injecting these glitches. In a similar fashion, you probably need to make modifications to the board in order to provide the power to a specific part of the chip.
And maybe to give you the other answer, even if you don't want to do these modifications, you can use things like EM pulses, so electromagnetic pulses, to actually gain, sort of similar capabilities without actually modifying the board too much.
I mean, it does emphasize the need for physical security as much, right?
Yeah, which is sometimes not available, right?
Right.
Yeah.
Thank you.
Thank you.
Thank you.
Do we have time for?
Yeah, we have all the time in the world.
Well, we do. I'm not sure about.
So I had a question about how you can use FI for chain of trust. When you're using chain of trust and secure boot, so let's say we have a stager, we have, say, an initial boot ROM, and we have a separate bootloader, which is eventually loading the kernel. So we can use FI to maybe bypass the first check, but how do you consistently do it across 3 separate stages?
No. Okay. Sorry. I understand the question. So the question is basically, so there are these, this chain of trust, and then every stage you have an additional check which checks the next stage, right? So basically, that's not the goal. We're not going to try and attack all those stages. We're just going to attack, for instance, the first one. Then we provide a modified second stage, which either has our key in it, perhaps, or doesn't do the check. And then we actually no longer need to check. So actually, we've completely broken this chain.
So does the process change if you're fetching the key from maybe a secure enclave or something like that?
Sorry, just the process change when?
You're fetching the public key from the secure enclave.
Depends where the secure enclave is. If it's external, for example, it has a huge impact. If it's inside, then, in the end, the integrity of the public key, that's what's important. So from an attack point of view, it does not matter too much if it's an OTP or in a secure enclave, as long as it's not changing. Because if you can change the public key, then you can write your own signature. So that's the most important part, that this public key does not change.
Yeah, so I think it will change some of the specifics you need for the attack, but I think some of these other parts may be unchanged, will be unchanged.
Thank you.
Thank you.